Hello, friend. Today I would like to share with you a special topic on static friction in rolling. This is a very interesting topic. Actually, I find in my class, many students have misconceptions in this issue, and even some famous textbooks also have misconceptions that mislead the student. So I would like to first briefly show you how to describe the rolling without sleeping. This is the ideal situation that rotation is coupled with translational motion through a cylinder rolling on top of the road surface. So the basic equation here we used when there's no sleeping is the displacement in the translational motion can be measured by the circumference of the cylinder, that is the radius of the cylinder times the angular displacement equals the translational displacement. Because the translational or linear displacement is measured by the circumference of the cylinder. So that's why we have this R times the angular displacement, which is basically the length of the arc, or the circumference of the cylinder is equals to the displacement. So if we do the first order derivative over time, we get the equation R multiplied by the angular velocity, omega, which is the first order derivative of theta, equals the velocity, which is the translational velocity or linear velocity. So similarly, if we do the second order of derivative of time, then we get R times theta double dot equals S double dot. That means R times alpha, which is rotational acceleration, equals A is the linear acceleration. So these three equations are basic equations to describe the rolling without sleeping. The translational motion is measured by the center of mass, which is on the axis of rotation here, axis of rotation. So with these equations, we will be able to solve generally all the rolling problems without sleeping. So let's see the first example. If we have a cylinder rolling down an incline without sleeping, then the cylinder is rolling without sleeping, then that means the static friction drives the rotation of the cylinder. So that's the rotation will follow the translational motion that go down from the incline along the incline surface. So many textbooks said that you can use the energy conservation, mechanical conservation to solve this issue because the friction does not do work. We will show here the conclusion of energy conservation is true. However, the assumption that friction does not do any work is wrong. So first we do some analysis. So based on this kind of setup, we find two forces along inclined surface. The driving force is the components of the weight along inclined surface, which is going down slope. And the other force is the friction, static friction between the cylinder and the incline, which is backward. So the weight component, mg sine theta, is basically the driving force for the translational motion because it's passing through the center of mass. And this force does not cause a torque to let the cylinder to rotate, but the friction is actually acting by the rim or the bottom rim of the cylinder, and it has the torque. That's why friction is actually driving the rotational motion. So friction impedes the translation because it's backward, but it drives the rotation. That means the work of the friction is actually diverts the kinetic energy from translation to rotation. So that's the key. You can see here the work of the friction is not actually dissipated, meaning that it does not consume mechanical energy and transform it into heat. Instead, it actually converts the kinetic energy from one form to another form, meaning from translational form to rotational form. So this is the key concept here. That's why a lot of students feel confused because we have friction actually doing work, but without consuming mechanical energy. So let's prove now the mechanical energy conservation for this problem. So first you apply work energy principle to both translational and rotational motion. So the translational motion, the work by the components of the weight does actually positive work, meaning it's positive. And the work by the friction is negative. So that's why we say mg sine theta, which is the force along the inclined surface, and L is the distance moved along the slope. So the force times the distance, you get the work done by the weight. And the negative work done by friction is F friction times the length or the displacement of the motion, translational motion along the slope. So this is negative work. So that net work of the whole of the two forces is equal to increase of the translational kinetic energy, which is 1/2 m is the mass of the cylinder times v squared. V is the linear motion, the velocity of the linear motion, meaning the velocity of the center of mass. So this is the translational motion, the work energy principle applied to the translational motion. The second part is actually we consider apply this work energy principle to rotation. So the work done by the torque for rotation is the force times the lever arm, which is radius, gives you the torque of the friction corresponding to the friction. And L is the total translational displacement divided by radius of the cylinder. You get the angular displacement. So torque times angular displacement, you get the work for the rotational motion. The work of the rotational motion equals to the kinetic energy increase of the rotational kinetic energy. That means it's 1/2 I, which is the rotational inertia of the cylinder, times omega squared. Omega is the angular velocity. So you can see that this equation can be easily simplified to F friction times L, because R is cancelled, so equals 1/2 I times omega squared. Then we plug in this equation, the second equation, to the first one. We will find this mg sine theta simply equal to mg sine theta times L simply equal to mg times h, the height, because L times sine theta equals height. And this is a potential energy, and equals F friction times L, according to the second equation, equals 1/2I times omega squared. So this is negative. You move to the other side, turn into positive. So that you can see that mgh equals 1/2 mv squared plus 1/2I omega squared. So the meaning of this equation is that the total potential energy decrease will be converted into two parts of kinetic energy. The first term is the translational kinetic energy. The second term is the rotational kinetic energy. So that means the work of the friction is actually converts the potential energy, part of the potential energy, into rotational. So that diverts the kinetic energy from translational to rotational. That's why mechanical energy is conserved, because the work of the friction does not dissipate the mechanical energy. Instead, it transformed one type of kinetic energy into another type of kinetic energy. So we can see that in this problem, the friction force does work to the cylinder, but actually the mechanical energy still conserves. Okay, this is the first example. And the second example, we will see that how the direction of the friction changes dramatically with the circumstance. So, for example, so if we have a cylinder, and the cylinder is actually rolling along a flat surface, and this rolling is driven by a pulling force through the center of mass, that Fp. Because Fp is passing through the rotational axis, which is the center of mass, it does not cause any torque because its lever arm equals to 0. So the friction will be going to the backward because it is against the pulling force, and it is provides the driving force for the rotation. So here the analysis is like this: the motion is driven by a pulling force that is passing through the center of mass, which is the rotational axis. That's why it doesn't cause the rotational torque here. So the translation drives the rotation. In this case, the translation really drives the rotation. That's why friction impedes the translation. So the friction must be going backward. It impedes the translation because translation is the driving force. And it actually drives the rotation. It drives the rotation going forward. So that makes the rolling is actually consistent with the translational motion. Rotation is consistent with translational motion. So for the case B, what if we do not use the force to pull through the center of mass or the rotational axis? If we actually let the pulling force acting on the top rim of the cylinder, then we can see that the friction will change the direction. In this case, because it's driven by the top rim, that means rotation drives the translation in this case. It's totally different from the case A, which the translation drives the rotation. Now, in this case, the rotation drives the translation. That totally changed the direction of friction. Now the friction will impede the rotation. So it's actually going forward. So it actually accelerates the translational motion together with the pulling force, but it actually impedes the rotation. So, of course, in this issue, if you are not very sure about the direction of friction in case B, case A is relatively easy. Case B may be difficult for many students, but even if you're not sure about the direction of friction, you can just assume either way, either forward or backward. Then let your calculation tells you the final result. So now, with this kind of analysis, we can go ahead to do the calculations. The key here this is actually use the Newton's second law for both translational and rotational motion. First, we consider case A, situation A. That means the driving force is passing through the center of mass, which is, of course, the rotational axis. And first, we apply the Newton's second law to the translational motion. That means Fp minus Ff, friction, equals mass times A. A is the linear acceleration. So similarly, the rotation, the Newton's second law for rotation is the torque by the friction force, because the pulling force does not have any torque. So the net torque is the torque caused by the friction force. The friction force times the lever arm is R, equals I, which is the rotational inertia, times rotational acceleration, alpha. So because the rotational inertia for the cylinder equals to 1/2 m times r squared, so alpha, or the angular acceleration, equals A divided by R. So we can derive that this F friction times R equals 1/2 mRA. So then divide by A to both sides, we get F friction equals 1/2 m times A. And then plugging this equation to the first equation, Fp minus Ff equals ma. Then we get Fp equals 2/3 ma. So you can see now in this case, the pulling force is actually equals to 1.5 m times A. A is the constant acceleration, which is a linear acceleration. And the friction force equals only 0.5 or 1/2 of ma. So that means that the pulling force is 3 times of friction force. So for case B, we can see that translation motion is different, because now both the friction force and pulling force are forward. So we use F friction plus Fp equals m times A, acceleration. So rotational equation is like the pulling force, the torque caused by the pulling force is positive, is actually lattice rotational clockwise, and the friction caused the torque, that is caused the rotation, decelerates the rotation. So that is F friction times R. So the net torque equals Fp times R minus Ff times R equals the rotational inertia times angular acceleration equals 1/2 m times R times A. Yeah. So we can see with these two equations, we can solve for Ff and Fp. And interestingly, you can see now dramatically change the both direction and magnitude. So you can see now we can use smaller force to actually drive the cylinder to move at the same acceleration as the case A. But the pulling force is now only 1/2 corresponding to case A. And friction is also 1/2 compared to case A. So you can see that now. So simply by changing the action point of the pulling force, you change both direction and magnitude of the pulling force and the static friction. And this is very interesting. So to understand the physical meaning of these two situations, we have to understand that when translation drive rotation, friction is against the translational driving force to divert the kinetic energy from translation to rotation. But when rotation drives the translation, the friction goes against the driving torque to divert the kinetic energy from rotation to translation. So that's why, in this case, the friction and the pulling force dramatically changes the direction and magnitude. So the third equation shows that how the friction changes meticulously changes magnitude in the process of motion, and it's actually the magnitude is actually fit perfectly to the simple harmonic motion. So the cylinder of mass m and the radius r is on the horizontal surface and attached by its rotational axis through the center of mass to one end of the ideal spring with force constant K. The other end of the spring is attached to a vertical wall here on the left side. The cylinder is pulled back and released from rest. The cylinder rolls without slipping, meaning that static friction is coming into play. Prove that the system is simple harmonic oscillator, and express the frequency in terms of m mass, radius of the cylinder, and K, the force constant. Remember that here the ideal spring satisfies Hooke's law. The elastic force of the ideal spring equals negative K times x. X is the displacement relative to the equilibrium position. K is the force constant. Negative sign meaning the elastic force is always negative, is always opposing the displacement. So in this case, because the pulling force is actually passing through the center of mass or the rotational axis, it does not cause any torque. So that means the friction must against this elastic force, because the elastic force is the driving force for the translation motion. So friction must go against that elastic force and cause the rotation of the cylinder. So friction converts part of the work of the elastic force into rotational energy. If without friction, and this cylinder will not rotate, it just have translational motion. So in that case, then all the kinetic energy is translational kinetic energy. So all the work done by this spring will be converting into the translational kinetic energy. But because of friction, the kinetic energy is divided into two parts. One part is the translational kinetic energy. The other part is the rotational kinetic energy. So based on this analysis, let's see how we can solve this problem mathematically. Apply Newton's second law again to both translational motion and the rotation. So the two forces here we already analyzed. One is the elastic force of the spring. The other is the friction force. And translational motion, the two forces actually they are against each other, always against each other. The F elastic minus F friction equals ma. A is the translational acceleration, and that is negative kx plug in Hooke's law. FEL equals negative kx minus F friction equals ma. So for the rotation, so F friction times R, that's the torque, net torque, equals I, rotational inertia, times alpha, which is A divided by R, and equals 1/2 for a cylinder. The rotational inertia with respect to the center of mass equals 1/2 mr squared. So times A divided by R. So you get a 1/2 mRA. So both sides have R. So R is canceled from both sides. So that means F friction equals 1/2 m times A. So plugging in this equation to the first equation, you get the differential equation for the simple harmonic motion, standard differential equation. negative kx equals 3/2 m times a, where a is basically the double dot of displacement. Now, based on this equation, you can see that omega squared equals 2k divided by 3m. So friction proportional to acceleration in this case, hence effectively proportional to displacement, merging with the elastic force to obey Hooke's law. So this is a very neat example to show how meticulously the static friction can adjust itself to fit perfectly to the circumstances. Thank you for watching.